Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're happy today to have with us a delegation of 20 people, 2 professors and 18 students from the University of Cagliari in Italy. The professors leading the delegation are Professor Giusto, who's here to my right, and Professor Luigi Raffo. Professor Giusto received his PhD in 1990. And he's been a full professor of telecommunications at the University of Cagliari since 1994. Is that right?
Yeah.
He's won Best Paper Award and or a couple of Best Paper Awards, and he's been an evaluator for the European Commission and involved in IEEE standards and highly relevant to some of us. He's also the Italian head of delegation to the ISO-IEC joint ITUT committee known as JPEG. Without further ado, I'll introduce Professor Giusto, who will lead a series of lectures on the signal processing research at the University of Cagliari. Please.
Thanks a lot, Gary. Hello, everybody. I'll give you a short presentation of our university, and I'll try to explain how we are here in Seattle, and I'll give you an overview of what we are doing in our labs, and after I'll give the floor to my colleague Luigi Raffo for a short presentation of the Microelectronics and Digital Systems Lab, and after you'll enjoy 3 presentations by our students. So, where are you from? We are from an island in the middle of the Mediterranean Sea. It's a vacation land. It's kind of Hawaii for Italy. It's famous just for tourism. We don't have any major technological companies, but we have a large telecom operator based in Cagliari, but it's an Italian operator is without much visibility in the international scenario. And the University of Cagliari is quite old. It dates back to 1606, and we have today around 40,000 students and 11 faculties: medicine, engineering, economics, political sciences, physics, mathematics, and so on. We are with the Faculty of Engineering, of course, and was founded the last century as a Royal School of Mining Engineering, because Sardinia is famous for coal mines. Now they are not no more operating, but in the past was a good job opportunity for local people. And as a faculty, we have around 7,000 students divided into 6 different departments. Briefly, civil engineering and structural engineering, electrical and electronics, chemical, environmental, mechanical. And we have 10 different courses offering bachelor, master, and PhD degrees. And as a school of information engineering, we have around 150 students, new students per year, and decreasing. In the past, we had much more. It's around 300 new students every year. And we don't have a kind of, let's say, it's a closed number. So it's in Italy, it's free. You can you must enroll all the students that apply to the university. So in the past we had a huge number of students. Now this number is decreasing, but it's still quite high. And we offer degrees, bachelor, master, and PhD degrees in electronic, telecommunications, and biomedical engineering. Our department was established 10 years ago, and we are today 40 permanent researchers at different degrees, 12 full professor, 11 associate professor, and 17 assistant professor. And we have around 50 people, including contract professor, postdoc, and PhD students. The research activities in our department are relevant to almost all the areas in information engineering. That is automatic controls, circuit systems, computers, electrical drives, electrical measurements, propagation, microelectronics, power system, telecommunication, digital media, and so on. And well, why we are here? Since some years we are organizing this kind of tours to the US to offer to the students a view about companies, universities, major events, and so on. And we started in 2001 going to New York to visit the TJ Watson and the Bell Labs. And after the following years, we moved to California because in New York in January the weather is really, really, really cold. And we are coming from a nice island where the weather is good all over the year. California, so we traveled to mainly Bay Area, and also we visited the CES, Consumer Electronics Show in Vegas, sometimes. So this year we decided to check, and we organized a visit to Seattle because it's Microsoft is based in Seattle, and Microsoft is the primary industry in our field. And we're visiting also Boeing, which is say the main industry. It's not our primary say topic, but it's anyway it's quite interesting for us to see what they are doing about electronics for aviation. We are 18 students from our master courses in electronics and telecommunications, and we are 2 professors. My colleague is Luigi Raffo. He's full professor of microelectronics and digital systems, and he will give a short overview of his lab right after my presentation. This is a brief schedule. We have 3 speeches by our students. Simone Secchi will talk about runtime adaptive resource allocation and balancing on nanoprocessor arrays. Paolo Pintus will illustrate a topic on ElectroEncephaloGrams, signal analysis and pattern recognition. And the last one by Alice Orlich is on image-based authentication. A few words on my lab. The lab was established in 1998. It's part of the Department of Electrical and Electronics Engineering, and is part also of the Italian National Consortium for Telecommunications. It's a huge consortium that is made up of all the universities in Italy working in the telecommunication areas. MC Lab has a staff of 14 people, including professor, assistant professor, and PhD students. And we are investigating different aspects in image, video, and networking, and also some industrial vision applications. Regarding images, well, we are involved in JPEG standardization. We did some work on error resilience and concealment. We are working on authentication using pictures. We are also working on 3D data compression and picture quality estimation and some kind of system for archiving data, and it's in particular we are working on developing a system for archiving the pictures coming from air traffic control systems and so on. Regarding video, we are involved also in standards. We are participating to the MPEG activities. We are working on quality of service based communication, resilience and concealment, segmentation, and also kind of interpolation using iterated function systems for slow motion replay of video sequences. Regarding networking, we are mainly working on quality of service and traffic modeling. Also investigating ad hoc networks, next generation networks, and so on. And the visual inspection, we are at present we are working on non-destructive testing together with Alenia. We are analyzing the wings of the Boeing 787, and we did some work also on thermal images, analysis of wood products, core classification. Cork, it's one of the major products of Sardinia, so we did some work on classification of cork, and we are cooperating a lot with industrial companies. The major source of fundings come from industries, so it's not basic research, but it's more applied research, and you can find a few of these companies we are working with, and Abenet is a local company dealing with voice over IP systems. Alenia, Tiscal is the local telecom operator. Vitrociset is a major industry working on the air traffic control systems. Ericsson, IBM, ST, and so on. And we also have funds from the European Union, the Italian Ministry, and the Sardinian Regional Administration. Okay, I think it's enough. And if you have any question, otherwise I'll give the floor to my colleague, Professor Raffo. Okay. Thank you. Se non ve lo facciamo l'applauso voi, non credete mica di comprarci così. Tieni. Ti serve il favore? Perché c'è anche
Cosa ne sapete se era volontario?
E appunto sul taglio.
Ok, it seems okay. I need Okay, my name is Luigi Raffo. I'm the leader of the laboratory of microelectronics at the university, at the Department of Electronic Engineering of the University of Cagliari. And I have a few slides to present our activities. After the presentation of Daniele, it's not important to say where we are, but probably it is important to say who we are. We are 12 people, 3 permanent positions, 3 PhD students, 3 PhD, and 6 PhD students, and several undergraduate students. It is much more important to say what we do. Essentially, we develop research project. We develop industrial research project. We provide several undergraduate courses in the field of digital design and biomedical device design. And we give the opportunity to more than 20 students per year to perform their thesis activity in our lab. Here there is just a list of our courses. I don't think it is important now to explain each courses. For me, it is just important to say that we perform activity in, we teach courses in digital electronics, digital signal processing, embedded system, DSP architecture, and microelectronics. What is important for me to show now is that in the corner of each slide there is a board or something practical. So this means that in every course we give the opportunity to our students to make a real experience in the field of electronics, and we are proud of it. Just a few words on our research activity. As you know, electronics is not by itself an application. It is a way to perform many different things, and so it can be applied to a lot of different applications, and we consider a lot of application. The common point of all this activity is that we want to have an improvement in performance or of something useful. So our research is not just for publish, but it is important to have an improvement in the quality of product and to give the opportunity of our students to have real experience in the field of electronics. Here there is a strange graph. I need probably more time to explain this graph and explain directly all the activity in our group. more or less the meaning of this graph is, okay, here there are a lot of application. Okay, we are interested to create a DNA chip, a network on chip, distributed VLSI system, biomedical equipment, AD converter, reconfigurable architecture, vision chips, many different things. But we use for all these applications the same method, the same technology, the same technique. So we have to be able to perform a physical chip design, analog design, digital RTL design, system design, system DSP design, and software design. And in some application, we have to put a sort of philosophical idea, so the bio-inspiration. Okay, and okay, the colors means okay, just to say okay, for biomedical equipment, we are interested to DSP and software and things like that. Anyway. The meaning of the graph is just, okay, these are the activities and these are the things we are able to do, okay? I go directly on some of our applications, some of our research. After there will be a presentation of Simone on one of these research, so I don't need to go deeper. It seems I see some similarity between our smart sensor design and the presentation of Phil on the camera, because we are using smart sensor design to realize what we call smart camera. So we don't have as the result of our camera an image, but directly a number of features useful for a different application. In this case, for example, we have developed a chip able to extract directly all the edges, just the edges of the image and the direction of the edges. So you don't have the image, but you have just the position of the edges and the direction of the edges. This is useful, for example, for OCR application. Obviously, someone can say, okay, but why you need this kind of chip? You can do the same with the camera and the PC. But you are able to do the same task with a single chip, smaller, with a limited number of transistors, and a very, very, very small size and very small power dissipation. So it can be useful, for example, for portable application. Obviously, it is much simpler to work with the camera, but for special application, this can be useful. A completely different application can be, for example, biomolecular recognition by standard CMOS technology. Okay, we develop a DNA chip, so DNA chip are able to detect if the presence of a strand in a specific sequence of in a DNA strand. Usually this is done by fluorescent labeling, and after you have to send ultraviolet light, and you take the image and you process the image. You can do directly this task by using a charge approach. This is our approach, we patented it, and so we are going directly to measure the difference of charge when an hybridization takes place or not. And so we are able, in principle, we need a lot of time, but in principle we are able to create a sort of stick able to giving us the possibility to detect directly the presence of a sequence in our DNA, so to consider, for example, a test to detect a DNA disease. Okay, this is just the global setup with the fluidodynamics part. Okay. Another application is reconfigurable architecture. We have a project with ST Microelectronics on an architecture composed of a lot of simple units configured and interconnected properly to obtain the best performance on different applications of the same kind usually. Okay, so for example, there is a number of multiplier, a number of others, and you can organize them to obtain the best result for a global, for a whole set of application, of task of an application. Another idea is to use a distributed VLSI system. Okay, this can be interpreted by inspiration with swarm intelligence, but it is a long story, so I prefer to avoid this point. But just to say that we could consider to distribute a task on more than one small processor. And the idea is that to each processor is given a specific subtask, but we are able to exchange sub-tasks between a single processor to have better performance in terms of time and also in terms of best exploitation of the calculus resources. Okay, this is just the distribution of a load of all the processing unit. This is just a presentation of a project we have funded. We have through a grant from European Union. It is a big project. We have a small part of it. It is oriented to have on a single chip more than we can say a number of processors, and our task is to help to connect this processor not with a bus structure. Okay, this is the list of the participants. Okay, our task is just to interconnect all the processor by using not a bus, but using a sort of network on chip. Okay, so the network on chip is composed like every network of computer by a router, by a network interface, and we have to realize all these modules to allow all the processor on the same chip to be interconnected, not through a bus structure, because the bus structure is a bottleneck for computation in our case and for a so large system. Okay, just a few words on DSP-based system. We are working on blind source separation by using a DSP from Atmel. It is not strictly a DSP because it is composed by DSP and an ARM processor. It is called diopsis, the structure, and we are able to separate two sounds, two voices in a room, okay, two independent talkers for the usual cocktail party problem in real time by using this DSP from Atmel. And we participated to a contest with this architecture, and we obtained the second place. We hope to win the next year. No, not. Okay, I have nothing to say more, and so I think we can pass to Simone for the first real technical presentation, not our blah blah. Okay. Okay, we can go. Okay, Simone. Sì. Finale, giusto?
Devo mettere quell'affare.
Faccio il microfonista. La scolatura.
Ok. Good morning, everybody. I'm Simone Secchi, and today I will talk about an innovative approach to the design of a parallel computing architecture. And this work is a still in progress work and is performed by the Microelectronics group at the Department of Electrical and Electronic Engineering at the University of Cagliari. Okay, everybody knows that in the latest years, a big effort has been spent on the development of parallel computing architectures, because as everybody knows, the Moore's law made become more evident the limits of sequential structures, sequential architectures, and so the research work is trying to develop these new strategies as parallel computing architectures. Okay, this is a brief outline of what we are going to see. And first, we will give some general definition. There is an introduction, and then there are some nice stuff on literature architecture, and together with a commercial one proposed by the Pico chip. And the main part of this talk is based on the research work of the Microelectronics group. Okay, some general definitions. In 1966, Michael J. Flynn proposed a classification of computing architectures based on the ability to execute different instructions at the same time, being each instruction based on different data streams. And so you have 4 categories. The first one is the single instruction and single data, which is, of course, the classical model of computing structures. There is a monolithic data path, which performs a single instruction for each clock tick. And then you have the multiple instruction and single data, the single instructions and multiple data, which are a trivial generalization of the first one. And the multiple instructions and multiple data is the most important classic category referring to this talk, because you have that in a single chip, you have different computational units, which works independently one from the other, and you have the ability to exploit different kind of parallelism, so such as thread level parallelism or instructional level parallelism, and so on. Data level parallelism as well. Okay. The state of the art, there are several attempts to perform this objective. And you have architectures oriented to exploit instructional level parallelism, like the superscalar architectures, the VLIW architectures, the out-of-order architecture, and so on. And the last 3 architectures are oriented to exploit the thread level parallelism, and so they are more suitable for maybe a general purpose processors. Okay. Tiled architectures are an example of a MIMD behavior, and so you have multiple instructions and multiple data. And the idea of a tiled architecture is quite simple. It's about taking few computational units, not few, you're taking several computational units, maybe hundreds, and put them into a single chip and make them work on a single task, each on a single task. Okay. Here's some stuff on literary architectures, and so you have the raw machines. I'm not going to talk about this because the time it's not so much. So there are the raw machines and the remark for a coprocessor designing. Okay. And together with a commercial solution provided by the Pico chip company, which is an English company, and it's called the Pico array. And you can see that this is, by this picture, that you have the tiled architecture, because there are several computing units interconnected by switch modules and Pico bus and so on. Okay. Okay, let's take a look at our proposal. The target of this research work is to to exploit different kind of parallelism and to break through the market of general purpose processors, because we have to perform different kind of control strategies, such as centralized control strategies, as you can see, or decentralized control strategies performed by the cooperation of single computational units, as I was saying before. the main tasks of this architecture are to exploit, as I was saying, different kind of thread level parallelism, instruction level parallelism, and data level parallelism as well. And this architecture is aimed to reconfigure to exploit a dynamic behavior, because it has to reconfigure at runtime, and this is the main important feature of this architecture, of this model. And so you have the third task is runtime adaptive resources allocation and balancing, of course. Okay, this is a schematic view of the architecture. You have You have, at the center, you have the nanoprocessor grid, which is composed by several nanoprocessors, several computational units, maybe hundreds of computational units. And then you have the dispatchers modules, which are the DS1s. And the dispatchers modules connect the nanoprocessor grid with the centralized control unit, which is called the scheduler. And then you have some central storage units split in different modules, and there are the caches, of course. Okay. There's a problem. Sorry. Okay, there's one slide missing, but I will talk to you. Okay, you have the central unit, the nanoprocessor grid, is the basic element of this structure, because it's, of course, the computational unit. And each computational unit is quite simple. It's a kind of reduced instruction set component, and contains an arithmetic logic unit, and 16 register bank, and fetch and store units, and so far. Okay, each computational unit contains implement also different layers of computation, because you have the computational layers, of course, which is the first layer, and you have the storage layer, because each of these nanoprocessor has also local memory, split different instructions and data memory, exploiting the Harvard model. And there's also an interconnection layer, because each nanoprocessor is connected to the 4 neighbors, and so there's an interconnection layer, of course. And the dispatchers modules, which I think they're missing too. No, okay. Okay, first we'll take a look to the caches module. Okay, the caches module are the global storage units, and you have the need to put these caches in this architecture, because the dispatchers has to fetch instructions and data from these units, and splitted modules make the architecture able to make more read-writes instruction in the same cycle, serve more dispatchers in parallel, and so you have the ability to handle the thread level parallelism in this architecture. Okay. The dispatchers, as I was saying before, this module is a kind of interface between the nanoprocessor grid and the central control unit, which is the scheduler. The dispatcher has to fill the grid with instructions and data as well, and has also to send back information, control packets, and implement control strategies with the scheduler. In fact, there's in this slide you can see there's a dedicated channel between the dispatchers and the scheduler. And so this channel is used with control packets and feedback information from the grid, from the allocation process. Okay, and you can see here that the main task of the dispatcher is to translate inter-task dependencies found or provided by the compiler or maybe the programmer, if it's required, and to translate these interdependencies in inter-nanoprocessor dependencies. Because once you have allocated the task into the grid, this task is performed by several computational units, and so the inter-nanoprocessor dependencies are handled by the dispatchers, because you have to implement a block and block command strategies, like in in parallel computing, of course. Okay, the scheduler is the centralized control strategy, control unit, and the main tasks of the scheduler are to maintain global system status information, because this architecture has to be fault tolerant in referring to fault in allocation process, and so you have to maintain the status of the system. Another task is the resources allocation, because the scheduler has to decide for how many processors allocate to one task, and something like this. Okay. And the scheduler is also to receive and handle feedback information to and from the dispatchers, of course. And these are the main tasks of the scheduler. Okay, here's an example of an allocation process. You have the scheduler as threads information, and for example asks to the first dispatcher to allocate, let's take an example, 5 nanoprocessor. Okay, so the dispatchers asks to the first borderline nanoprocessor to allocate a linear chain of nanoprocessor to perform to the instructions of this task. And so here's an example of a successful allocation, because each of these nanoprocessors asks to the neighbor to create and realize the chain, and you have the 5 nanoprocessors are being allocated to serve this task. And then the dispatcher sends back to the scheduler some feedback information and control packets as well. And okay, and that's the allocation process. You can see that it's quite simple to see that from this example, you have that the maximum number of executable parallel tasks is equal to the name of the dispatchers, because to the number of the dispatchers, because at each clock cycle, you have that dispatchers handle just one task. And so if you are, for example, 4 dispatchers, you have the ability to process 4 different tasks at each clock tick. Okay. Here's another example of the allocation process, but this one is not successful. And so you have, like we were seeing before, the allocation, the scheduler asks to the dispatcher to allocate 5 nanoprocessor. The dispatchers asks to the first nanoprocessor on the grid to allocate the chain, but let's suppose that the 4th nanoprocessor is unavailable at this moment, and so a fault occurs. Okay, the dispatcher has to send back to the scheduler the fault information and sends back an error packet. And the scheduler decides to, the dispatcher tells that it's able to confirm a chain of 3 nanoprocessors. But the scheduler decides to, for example, deallocate the chain allocated by the first dispatcher. And the scheduler decides also to ask to the second dispatcher for an allocation of 5 nanoprocessors. And the second dispatcher create the chain as well as we have seen before. Okay. Finally, there's a simple example of a parallel algorithm, which is the computation of a simple monodimensional discrete cosine transform. And you have the algorithm written here. This algorithm can be written in C code, in a simple C code like it's shown here. You have 2 loops, an inner loop, and red lighted in the picture, and an outer loop, which is the second loop, of course. And we are able to define, for example, the inner loop as being the elementary task, and so you can see that this is a quite simple multiplicate and accumulate instruction, because you have the multiplication between C and X, and then you have the accumulation on Y, epsilon. Okay. Okay, this is a simple example of an algorithm, and each of these tasks can be allocated into the grid with a chain, with a linear chain. Okay, here are some conclusions, because in this talk we have reported an innovative approach to the development of parallel computing architectures, and this architecture is quite an high potential one, because the target the target of this work is to develop an architecture which could be able to take place in the general purpose processors market. And of course, you can see that the collaboration at dynamic time between the different nanoprocessors is a quite high potential idea. And so anyway, the work is still in progress. So that's it. Thank you. If there are any questions, okay.
So I'm wondering what the granularity of the task is on the nanoprocessor. So you said
Okay, maybe I'll check.
the inner loop there.
Okay, this one.
Yeah, for example, I guess that's would be typical.
Yeah, it's this is a quite specific algorithm because the monodimensional discrete cosine is a parallel algorithm, as I was saying. But the coding of this inner loop is quite simple, and so you have that, for example, 5 or 6 maybe nanoprocessor can be allocated to serve this task.
So each nanoprocessor.
No, you have for the red lighted task.
What do they call them?
Okay, for the red lighted task, you have to allocate a chain of nanoprocessor.
Oh.
For example, 5 chain, 8 chain,
For
something
just
like.
for the inner loop, the red line.
Yeah.
So each what do you call them? Each node.
Okay, each nanoprocessor.
Nanoprocessor
Uh-huh.
does the same task, basically the same code. So is there a need to broadcast the program?
Yeah, you have to
Identical?
perform a communication, of course. You have to send data and instructions between nanoprocessor. And
Is it
you have the,
difficult to have them all common? Like they all do the same task, just with different data?
with different data, of course. Within a single task, you have that the chain, each nanoprocessor of the chain performs a single part of the task.
And is
I mean, this is an exploitation of instruction level parallelism.
No, each processor performs a different part of the algorithm. Each processor is able to perform, for example, a multiplication and accumulation. With respect to your question on granularity,
yeah.
Each processor is able, for example, to perform a sum, a multiplication, a multiply, and accumulation, and each different processor work on different data and perform a different task.
But but if they're all doing multiply, accumulate, for example,
Sorry?
they all do this. So they have
Not in this. Each processor is all the processors are the same as the structure, okay?
Right.
But in the same time are not performing the same operation.
okay, but they have storage, and there's instructions memory, and there's data memory, right?
Yeah.
So the instruction memory, you have to put in the program that the nanoprocessor needs to execute.
Yes.
Are those all the same?
That's
No.
Where is a cache?
Yeah.
Where each.
Okay, in this picture you have the global caches, but the instructions executed by the single computational unit are.
To each unit, which is the task to be performed. The schedule is another schedule.
Okay.
No, I can continue. Sorry.
I was saying that each nanoprocessor has its own instructions in the local memories.
Right.
The local instruction memory.
Right. But it seems like for your example of doing a dot product, for these 5 nanoprocessors, you basically tell them all to do the same thing except different kinds of data.
It is a very simple example, yes. Probably we have to change example, yeah. No, yes, because in this example, more or less, each processor do the same thing, yes. I agree with you in this example. But in general, no. Okay, yeah.
It's okay. Is it okay? Okay.
It seems like the data is
I
different.
didn't hear.
It seems like each processor is dependent on its previous processor for the data.
Yeah.
So how parallel is it? I mean,
How parallel?
Yeah, because it seems to be.
Okay, the parallelism is exploited between different chains. Within the single chain, you have the first nanoprocessor has to send information and data, instructions and data to the second one, and then the third one, and so far. Is it okay? Another question? Okay, thank you. And then the second one of us. Okay.
Abbiamo fatto qualche domanda?
No, questo è messo tranquillo.
Sì, non sto cagando.
I'm Paolo Pintus. First, I would to thank you, the Microsoft, to give me the opportunity to talk the objective of my thesis. The objective of my thesis is to talk about the prediction of epileptic signature in epileptic subjects. First, I do to talk about a little history of the electrophysiology. The first study about the electrophysiology was started by the Italian Luigi Galvani and Alessandro Volta. Luigi Galvani was the first that studied the electrical transmission in nerve of a frog. Only in 1924, Ansberger has been able to measure the voltage between two different points of a skull. A very important development in the study of electroencephalography is the employment of digital technology. The digital technology has permitted the use of more suitable and detailed elaboration. The use of more powerful computer has permitted the use of a more suitable and more detailed elaboration. First, is necessary to talk about the kind of signal in electroencephalograph. The electroencephalograph is a superposition of 5 different kinds of waves: delta, theta, alpha, beta, and gamma waves. The waves provide from different areas of brain, and each waves can prevail over the other waves. Therefore, the evolution parameters are the frequency. The frequency is the parameter that permits to distinguish the different waves, the amplitude, the morphology, and the topography. The different areas generate a different kind of signal. In this slide, we can see the beta, alpha, theta, delta rhythm, and the spectra representation. The gamma band is over the 20 Hz. In this slide, we can see the voltage from different area, from 18 different areas of brain. The electroencephalograph is not one signal, but various signal. The electroencephalograph analysis is important to the diagnosis of many pathologies like Alzheimer, Parkinson, epilepsy, and multiple sclerosis. The framework of my thesis is the prediction of the epileptic signature. According to some physicians, it's possible to predict epileptic signature studying the synchronism of the cell in a brain. To understand the problem, it's more important to understand the kind of signal and the kind of communication between the different area and the different cell of brain. In general, the cells collaborate in a good order and seem to have a good synchronism. In epileptic subject, the cell of brain seem to have an anomalous synchronism. With the study of this synchronism, it's possible to predict an epileptic signature. In epileptic subject, the organism generates an electrical signal to stop this anomalous synchronism. It is like a shutdown and reboot of an operating system. To stop an possible seizure, it is used a vagus nerve stimulator. Vagus nerve stimulator is a device implanted under the skin on the chest. This is a pulse generator that generates an electrical signal that stop a possible seizure. In this slide, we can see the devices on the chest and the vagus nerve on the left. The method used to predict to study signal are correlation and spectral analysis, self-information, multi-information, nonlinear analysis, and multivariate data analysis, PCA and ECA. Correlation is used to describe the synchronism between the different areas of brain. Self-information and multi-information are derived from the information theory. We can think the brain like a signal generator. If a signal is more likely, the information is less. Vice versa, if the signal is less likely, information is more. Nonlinear analysis is used to describe the complex structure of the brain. And multivariate data analysis is used to describe the different kind of signal in a multidimensional state space. The principal component analysis is used to describe the multidimensional state space with the principal component, orthonormal principal component. ECA is used to describe the signal with statistical independent component analysis. In this slide, we can see the classical method. The classical method consists in the signal acquisition, the codify. After that, the signal is codified with Weyler transform or discrete Fourier transform to enhance the characteristic of more interest, like frequency, delay, and so on. After that, it's possible to predict an event and to apply our algorithm. In this presentation, here I have reported two works. The first was by Arnold. Arnold represents the signal proving from different areas, the left area and right area. And he measured the synchronism between the different areas. In each area, it's placed 10 sensors. If a pixel in this matrix is darker, the different areas are more correlated. If the pixels are brighter, the different areas are less correlated. In this slide, we can see a selection of these metrics. From picture 1 to picture 8, we can see in the left area, the left area is more darker, and this is the synchronism before an epileptic seizure. From picture 9 to picture 14, the synchronism seems to vanish, and in picture 15 to 16, we can see the epileptic seizure. The study of the synchronism from picture 1 to picture 8 can permit the prediction of the epileptic seizure. Another work, the other works is by Martinelli. Martinelli represents the signal in a 16-dimensional space and select the three principal components. After that, he used a nonlinear parameter to represent the seizure root plot. The seizure root plot is a figure in which we can see the normal condition and pathological condition. The normal condition is represented on the cluster in the corner. And the pathological condition is represented along the diagonal. The use of the... It is possible to predict an epileptic seizure when a point go out from the cluster. It is possible to predict an epileptic seizure about 4-6 minutes ahead of time. In my thesis, I want to give my contribute to improve the method used by Arnold, and I want to make a new algorithm and a new representation of my the data from the brain. For this work is necessary interdisciplinary skills. The medical skills are the expertises in visual electroencephalograph analysis and characterization of the epilepsy. There is many kinds of epilepsy. In the engineering skill are the representation and the signal, and create a model, a mathematical model of the signal. After that, it is important the analysis, the signal analysis, and the pattern recognition for the prediction, for a good prediction. And after that, we want to implement this algorithm on ARM DSP. The perspectives of the implementation on ARM DSP to realize the electronic stimulator or automatic system to administer drugs. Let me finish. Questa è la perla. Any questions?
Sì, certo. Questo perché c'è anche prendi la sua. Okay. Good morning, everybody. I'm Alice. I'm going to present our work about mutual image-based authentication with JPEG 2K in wireless environment. First of all, I speak about security problem with some example of graphical password, and after present our solution that is based on ABA password and image scrambling with some result and the conclusion. All of us know how is important now with the diffusion of web services like e-commerce and home banking, the computer security. To ensure computer security, three of the most important requirements are the authentication, privacy, data integrity. Most of the current system are capable of ensure only weak authentication, where only the identity of the user is guaranteed. while most of advanced solutions have been proposed to guarantee mutual and strong authentication, where the user authenticating itself to a server and that server authenticating itself to a user. These systems are based on an encryption algorithm that often require specialized hardware, like as tokens or smart card. Privacy and data integrity are usually performed with networks protocol. The increase of wireless connectivity require the implementation of this feature, and several experiments show that image-based authentication with technique of watermarking or image scrambling grants all of these requirements. Here there is some example of the system based on graphical password, like Deja Vu, that require the identification of random image, and A-Ways E that require the identification of a correct pass image sequence, but all of these techniques are capable of guarantee only the weak authentication. While we propose a challenge response scheme that ensure the authentication security at application level and consists, we already said, of ABA password and image scrambling. The first phase is the phase of registration that consists in generation of the scrambling key and generation of the IBA password. The generation of scrambling key is made from the server, and the scrambling key is transmitted only during the registration phase, and it is shared by both server and client. And while the IBA password, that is the visual password, authentication password, is the real password that we use for the authentication. The creation of the ABA password is done with the following step. The server shows a large set of images randomly selected from a database, and the client have to choose a K-pass image, and for each image pass detail. All of this phase is done only over HTTP secure connection. After that, during the authentication phase, the application window is divided in K grids, each made of H shells. The user have to identify K-pass image among n images and K-pass detail for each image through the interactive zooming process. The visual password is transmitted only during transmitted step by step to minimize the risk of sniffing. To evaluate the security of the IBA password, we can calculate the number of the different configuration with the limit on the number of zooming steps, that is P. We compare the 4 different types of password: alphanumeric password, Deja Vu with 2 different number of images, VSKey with a different number of images, and IBA. What we can see is that the number of possible configuration is always higher in the case of ABA password. JPEG2K and JPIP are used in order to transmit image portion that is required at each step. The base element of an image is the tiles. Each tiles is coded with 5 decomposition level and 6 quality layers. To evaluate the scalability of the image, we need to to do a combination of 3 parameters that are the number of tails that we have to transmit at each step, the resistance factor, and the quality layer. The phase of image scrambling. During the phase of the image scrambling, the scrambling key is used from the server to encrypt all visual information. Several image scrambling techniques have been proposed, but their computational complexity is often high. We propose a system that is based on 3 stages of pseudo-random permutation in the wavelet domain. The first block provides for a pseudo-random sequence generation, generate 3 sequences from the scrambling key, image sites, and wavelet levels. In the other 3 blocks, we have in the first provides for the permutation of a coefficient in the LL subbands, while the other 2 blocks provide respectively for the permutation and for the sign inversion of all the other subbands but LL. To evaluate the encryption efficiency, we use 10 different images with 3 different levels of detail, with 3 different detail levels, and we can see that when we do a correct when we have a correct descrambling, the efficiency is good, while in the case of wrong descrambling, the PSNR is always about 15 dB. Here we can see also the same results. In the case of without scrambling, the resolution of image is very good. Is better, of course, in the case of level 1, and with the correct descrambling, the resolution is a little less, but anyways we are capable of understanding what image was transmitted. With the wrong descrambling, it is impossible to understand the image. Here are the results. We can see also that, of course, is the computational cost is higher if grow the number of permutation, grow the computational cost at the time for scrambling and descrambling. To evaluate the security, we have a case of no scrambling, scrambling with a key of 30 character, and scrambling with a key of 15 character. Don't seem, but all curves grow a little in the case of scrambling, but there is a value after a limit value. After this value, the increase the steps is not useful. The security have the number of configuration don't give us more security. In conclusion, we can see that the proposed system offers a strong protection because attacker to penetrate the system have to take over both key, scrambling key and visual key. It realizes the better trade-off between security, data transfer, and usability. The complexity is minimized, and the hardware upgrade is not required. That's all. Questo.